Okay, here we go. This is lesson number 4. Graphing. Logs, and I'm going to call them logs instead of logarithms because it's short, right? And we're going to start with one basic shape, two basic shapes, two. We'll do it. Y equals log base b of x. Okay, notice there's no transformations here. It's just log base b of x. And I'm going to tell you that b is more than 1 for this particular picture we're going to make. And we're going to do a table of values here. And we're going to answer two statements. We're going to answer as x. It's our end behavior statement, but I don't really want to give it away quite yet. Okay. I left off the number on purpose because we got to talk about it before we fill in what number is going to go there. Okay. I'm going to highlight some of the important things here. Okay, the base is important to describe the picture. Think about, there's a reason we evaluate our logs before we graph them, because I'd like you to be able to plug in x values and evaluate in order to plot points instead of just memorizing some points. I want you to actually understand why. So let's think of some x coordinates that you can plug in. What can you plug in here and actually get a result? Okay, hold on. No, I like that choice. Let's put 0 here. And can you evaluate? All right, so that's log base b of 0. Can you figure out what that is? Why not I just put y and see if I can do it. Say that again? Not quite. Is there any y value that's going to make this work? No. No. Oh, you mean it's undefined? What does undefined get you on a graph?
A straight line.
A vertical asymptote. Yeah. What did undefined get us last unit? It got us a vertical asymptote. Undefined values do not exist on a graph. So that is not possible. In this particular case, it's a vertical asymptote. The only way you get a whole is common factors reducing. It's not a common factor. That's just undefined. That's a vertical asymptote. Every undefined value will be a vertical asymptote. Nothing. Okay? Oh, so we're going to put a 0 here, and I'm going to put a little plus, which means from the right, because I'm tired of writing from the right. The plus means from the right side. Let's figure out if we can plot some more values before we answer our end behavior. Yep, that's 0. Okay, so I drew my vertical asymptote. What else could I plug in? 2. Okay, so we're gonna try it. Don't write it yet. Log base b of 1.
Wait, should it be a perfect square?
Almost. Can you figure out what y is?
0.
Oh, 0. Okay, that one works. I left a line on purpose, so if I plug in 1, I get 0. Right, you're trying to figure out what values can you actually plug in and get an answer. So that one worked. What's something else? Someone said a perfect square. Maybe. You're kind of on the right track.
Perfect.
So what if I put a 2 here? B to the y. Not really. Like, it's something. I just don't know what it is. All I know is that my base is more than 1. Okay, so if we plug in -1, hold on. That's an exponential graph. Is this thing ever going to be less than 0? No. They're just reciprocals. That's all we get. We get close to 0, but not 0. So that's not going to work.
4?
Hold on. I'm going to add something to this. Domain. We just realized that I can't plug in negative numbers here. So my domain is going to be a 0 to positive infinity because I cannot plug in any negative number. They're all doesn't exist, not possible. So that asymptote's my divided line here. I can't go to the left of it. Okay. I'm going to give you a hint. So what are my powers of b? B to the first. B squared. B cubed. B to the 0. B to the -1. B to the -2. Those are my powers of b. What if I actually decide to plug in, let's write maybe 1 over b instead. Can I just plug in one of those things? Okay, what if I plug in 1 over b? What do you get? -1, yeah. -1. You have to pick values, right? When you graph a square root parent function, you choose perfect squares because you can evaluate them. If I'm going to graph a log, I need to pick inputs that I can actually evaluate. So I'm going to do 1 over b. Well, what if I do b? Okay, let's put a b. B to what power equals b? 1. I mean, I could go on and on and on here, but that's enough points, right? 3 points. What if I did b squared? 2. Okay, so I'm thinking of what inputs can I actually evaluate. What helps us evaluate? Thinking of it as the exponential format instead. Okay, let's put these points on the graph and see what we can come up with in order to answer our questions. This is the easiest point because they're both numbers. 1, 0. The rest of them have to do with the b, or the base number. Well, our base is more than 1. So let's make this point to the right. B squared 2, it's just over here somewhere. Okay. So this one is b squared 2. This is b1. This is 1, 0. I don't know what b is. I just know that it's like bigger than 1. All right, now I have to plot. All right, I just got those two. Now I have to plot 1 over b. Yes. The y-coordinate is lining up, but the base, I'm just putting it to the right of 1 because it's bigger than 1. So yes, the x-coordinate is in a random spot. But I'm representing what it would look like. Okay, so look at the relationship. If this is x equals 1, this represents more than 1, which is the only thing I do know. Okay, this is 1 over b. That's going to be between 0 and 1. Which dot is closer to the asymptote? The one that's further down. Right, this dot is closest to the asymptote, which means as I connect these, that the asymptote is on the bottom. It's very similar to an exponential graph. The asymptote only applies for one section. So if I'm going to answer my infinity statement, I'm going to put from the right means put your pencil on the right side of the paper. Trace the graph. Negative infinity. The y-coordinate is pointing down.
Wait, why do you know it's that way?
Okay, so the plus means start on the right side of the graph, which actually, right side, finger on the graph. Trace it towards 0. X-coordinates are going towards 0 from the right. And so I trace it, and I keep going, and as I get close to 0 on the right side of 0, that's the positive side, the arrow is pointing down, so that's negative infinity.
Wait, so what's one of the
Wait till we get to a number, and then I'll come back. Okay, so now let's answer this. Trace the graph as x approaches positive infinity. So that's like this. That's actually positive. Quadrant 1, right and up. Slowly, right? It's going up slowly, but is there a horizontal asymptote? No, that means the arrow keeps going and going and going. And my range is, well, we have a bottom arrow and a top arrow. Bottom arrow, top arrow. It's all real numbers. All right, I think it would be useful to put some numbers on here, right? So we can see what this looks like with actual numbers. Let's make our base 3. Yep.
How do you know what the center is?
It always starts at the origin. Right? We just have to put the points in relation to the origin. A lot of times your vertex or your actual point is 0, 0. This particular graph, it's not, but that's still going to be the center. Okay, so y equals, let's graph log base 3 of x. So now I gave you a number. Where are the points going to go? We're going to answer the same questions. And so the base is 3 because that's going to affect my points. You need 3 points. I'd say between 1 and 3. The better you get, the fewer points you need. Okay. As x goes to 0 from the right, y goes where? As x goes to positive infinity, y goes where? That's what we want to answer. Yes.
If we're like writing the end behavior on a test, should we write 0 like?
I will probably give you the statements to fill out,
Okay.
and you will be filling out the actual blank that I left here.
Wait, is 1 0 always going to be a default point unless there's a stretch?
Uh-huh. And it will be even if there is a stretch.
What if there is a stretch?
What's 0 times 3?
0?
0. Nope. We only stretch the y-coordinate. Yes. Yeah. All right. So if I think about evaluating, right, what numbers can you put in? Because your parent is this. It's log base 3 of x. What can you plug in order to evaluate? Pick the numbers. 1, 0.
1/3 -1.
Yep, 1/3 -1. We're trying to plug in. What can you evaluate?
Oh, so is this what you're looking for here?
Well, you should have an equals in number 12. There should be an equals somewhere. You missed the equals. Right? All the rest of these things have equals. Okay? And let's go 3, 1. Oh, look at those points. I have the reciprocal, the 0, and the base. Yeah, there you go. Okay? And I'm going to say vertical asymptote x equals 0 because I know that I cannot evaluate right there. Okay, let's graph it. And plot it. 3, 1. I'm going to go ahead and put on here 9, 2, just so you can see it. That reciprocal point, it's really hard to graph. Just make sure that it's kind of a small change in x right there. Yes.
Will the vertical axis always be 0?
Almost always. With no transformation, yes. Can I transform it? Yes. And then it's going to move.
How many points do you need when you're like plotting a graph? One.
As few as possible. 1.
Yes.
We plot more until you get used to the shape.
Is this what you're looking for?
Yes, I'm doing that. Thanks. Okay, so I have my graph, and we're going to go and highlight a few other things that are important. I'm going to answer my questions. Which one? 1, 0. We're okay? Okay. All right. Let's answer. This one is the negative infinity. This one is positive infinity. Okay. This is an end behavior model. That top statement is not end behavior. End behavior means the ends of the graph, the left and the right arrow. This is an arrow in the middle. That's just vertical asymptote. That's just the behavior at the vertical asymptote. Means the region is negative because it's down. Okay, let's highlight what exactly do you need to put on this graph? Technically, 1 point. You might feel better with some other points, because that helps you make sure you get the shape correct. But this is the most important point, that 1, 0 point, because it's connected to the center of the graph. The center of the graph is 0, 0. This is the point that's just 1 unit over. That's where you start the graph. Then how do we get the rest of the points? It's those other 2 points right here. Notice that that's very similar to our exponential parent points. They're just in the other order. Okay? So when I'm looking up here, I need the center. Maybe the reciprocal and maybe the regular point. Yes?
Is that an A or a star next to the one?
It's a star. It's a star. That's like the most important point to get right, because it's 1, 0. It's going to be 1, 0 regardless of my base, because anything to the 0 power is 1. That's the point that's not going to change. The rest of them kind of shift or stretch a little bit based on the base. Yeah.
So this graphing, it's not really relevant to tomorrow, right?
No graphing tomorrow, right? But we got to learn.
Yeah.
There's none of this. There's exponential graphing. Okay, let's do some transformations. Here we go. Oh, you know what? Not yet. We're going to do this one. Example number 2, and then we'll do some transformations. Log base 1/4. Okay, my base is 1/4. How is that going to affect your graph? You still need, let's go with 3 points, right? We're not really sure about our graphing yet. Let's do 3 points.
Was that 4 over 4?
It's 1/4 is your base.
Hey, Crocs are cool.
Focus.
Neon.
Yes.
Okay. Log base 1/4. How is this going to affect my graph? opposite's not the right word, but I know, yes, yes. It's going to have a reflection from what we were expecting from the first graph. But the points are going to be just a little bit different because we had a base 3, and here we've got a base 1/4. Yes. Okay, so I'm just going to write it. What am I trying to evaluate? Okay. Well, 1, 0. Boom. I've got to get that point. It's going to be 1, 0. 1/4, 1. 4, -1. So when you evaluate logs, you're always looking for the powers. The powers is what you're looking for, the exponent. And let's go ahead and write the 0, right? That's my vertical asymptote. That's part of the parent function. It's part of the parent, because notice we don't have any AH or K yet.
So is the first one the parent function?
Yes, but notice how we had growth and decay shapes for exponentials, but the process was still the same? Kind of growth? Kind of.
Are we gonna have to say like, okay, this is a growth graph, this is a decay graph?
I don't think so. You should know it. You should know it because it helps you get the right shapes, but I don't think I asked you specifically.
So for this, the vertical asymptote would be someone else if there's x minus
Which we're going to transform it in a second. All right. Whoop. And graph. 1, 0. 1/4, 1. 4, -1. Okay, look at my arrow. The point on the top was closer to the asymptote. That's the part that's getting closer to 0. That's why we put more than one point on the graph until you get used to the shape. Notice it's the 1/4 base. My base was less than 1. Look what happened to the shape of the graph. It changed. Okay, so 0 from the right is actually pointing up this time. This one is actually quadrant 4. It's going down, right and down, slowly, but it's going down. Notice, I'm just going to put the point 1, 0, 1/4, 1. Look at the points. The 4, that's how you can pick out the base. You're looking at the exponents that are connected to it.
Just wondering, in what scenario would you create like a decay?
So growth and decay is only defined for exponentials. I say growth in quotes because it's like 4. It's up and right. So I'm like, okay, I can kind of think of growth here. I said kind of. Here, it's getting, the y values are decreasing. The y values are decreasing. It makes me think of decay. But really, growth and decay is an exponential characteristic. It's sort of connected to logs, but we don't really describe them that way. Yeah.
Is there anything in the equation that makes vertical asymptote always 0? Like it would change?
Yes, there is. It is this part right here. Okay? What gives you the undefined value? Plugging in 0. That's why the asymptote is at 0. Why do I graph nothing on the left side? I can't plug in negatives either. Okay. All right. Here we go. Let's put some transformations on it. Okay, turn to your next set of graphs. We're going to do transformations. We're going to do a graph and a reflection so we can see what happens.
So you wouldn't be able to do it on the left-hand side?
You can if you put a negative on the x, which would reflect this way, which we don't do. We just do this reflection.
Oh, so we're not going to do that.
No, we're not. All right, here we go. Example number 3. All right, log base 2 x plus 3 minus 4. Okay, base 2. Base 2 is going to help define the shape of the graph. Left 3, down 4. So I'm going to mark my center, right? My center is left 3, down 4. Okay, there's my center. Now I need to place my asymptote and my points based off of the center of the graph. And so my table of values is based off of log base 2 of x, right? Take away the transformations. Now do your parent points. Where'd the tape? There it is. I keep moving my graphs. Mine aren't taped in. Okay. Anybody else tapes up here? Okay. All right. Okay, vertical asymptote goes through the center. So my vertical asymptote, x equals -3, because it's the x equals. So my asymptote can move, it's just based on the transformation. Points. Oh, okay, so my base is 2, so I can do 1/2, 1, and 2. I can actually evaluate. Look what I'm evaluating though. Log base 2 y coordinate, right? That's what I'm evaluating. I'm just picking 3 easy points. Oh, there's no stretch. Just put your parent points on the graph. Now I'm going to give you your statements here though. 3 from the right. Notice how that changed from 0 because my graph shifted.
Would it be -3 or 3?
Oh, -3. Thank you. And we'll just label domain and range. Nope. Just like the exponential graphs, it's always there. That's where it is. Even for the rationals, our center was 0, 0. That's where the asymptote started until we moved them. Yes. Okay. 1, 0. And the base is 2, so it's the y values are increasing. So it's going to go 2, 1, 1/2 here. The points are pretty close, but notice that the point on the left, on the bottom, that's closer. And so the asymptote is going to be pointed down. Negative, positive. That's it. That's your graph. Yes. That's for me to mark the center so I know where I'm counting my points from. That's it. It's not a whole. It's just me like counting left 3, down 4 so I don't lose it. Because the graph, you're like, oh, I don't know where I started. Just to keep track. Okay, domain, -3 to positive infinity. Range, still all real numbers. Okay, we have 7 minutes. We're going to graph number 5, and then we'll call it a day. Or 4, sorry, 4. Number 4. Okay, y equals -2 times. So we're going to do 3 transformations, a, h, and k. Log base 1/3 x minus 1. Oh, I lied, just 2. You can do it. It's a 1/3, yes. So base 1/3, right 1. I should probably prefer to write this maybe in the order that I'm going to do this in. Reflect over y. Stretch by 2. Okay. Log base 1/3. Okay, that's what I'm doing. Right? Get a few points, put them on the graph. Oop. Oh, nope, it's not left. Man. Right 1. Okay. All right, try it. See what you get.
Let's see.
You want to see the top one? Yeah. There you go. Okay.
Excuse me.
The y, it always multiplies the y coordinate. Right? Our stretches are going to multiply the y. The only change on the x is inside the parentheses next to the x.
Gonna be on the quiz.
No. No graphing logs on the quiz.
Wait,
Just
are we reflecting over the y-axis?
yeah. Oh, I think my y looks like my x just didn't make it all the way over. It's going to look just like the graph above it.
Oh, okay.
Because look, this is what, hold on, this is what decay would have looked like. But it got reflected.
Oh, okay.
So yeah, it is going to look like that. That's what a reflection
Wait, then
does.
wouldn't that be a reflection over the x-axis?
Yeah, my x just wasn't like long enough.
Just making sure, so when you're plugging in points and finding the y, you only apply it to 1/3 x?
Yeah, because the up, down, right, left is taken care of with the new center. The only thing my shift didn't do is stretch it. That's why we marked the center. So when I mark the center, I'm going to go right 1, up and down, nothing. And then there goes my vertical asymptote. When I do this, I've done everything except times -2. That's it. That's the only thing I haven't done yet. And so when I do my parent points, okay, 1, 0, 1/3, well, I guess it's backwards. 1/3, 1, it doesn't matter. 1/3, 1. Because I was going to put it, I was going to do my y values in order, but that's silly. You should do your x values in order. Okay?
Oh, I did not.
And then I times by -2. Okay, so 1/3 -2. 3, 2. Notice that these points you have to count from the center of the graph. And so it's almost, exactly like the picture above it, just a different center. Slightly different points, except for the 1, 0 point. That point never does anything different. Stretching doesn't affect the 1, 0, because the y coordinate's 0. It doesn't change. Okay, your homework is the graphing worksheet. I guess that would be worksheet 6. I suggest trying to do some of it tonight.
Evens?
Yeah, you know, there's not too many on there. So evens, if you need more, do more. If they look different, try the different one.
Okay, wait, sorry. What did you say?
Your homework is worksheet 6 about evens. You need a few more, do a few more. If the question looks different and it's odd, do the odd one just to make sure.